All right, hello. Today's presentation is called Periodic Table Intro. And as far as chemistry goes, or all scientists really, but especially chemists, there is a wealth of information that can be had from the periodic table. You can use the periodic table to find information about individual atoms. You can use the periodic table to make useful predictions. You can use the periodic table to just as a visual that contains all of this information that if you know how to use it and you know how to identify it and how to get that information, I'm here to tell you, it's going to make your life as a scientist, at least in this regard, a lot easier. All right, it all starts with a guy by Dmitry Mendeleev, who was a Russian chemist. And basically, if you kind of look here, obviously his early table doesn't really mirror what we would see in today's modern periodic table. But we do really need to give a lot of props to Mendeleev for the early work that he did. And he was very instrumental in helping us to make the periodic table. All right, he was a Russian chemist, as I stated, and he developed a table, and he put his table together based on increasing atomic mass. And once again, if you kind of look at his table, but the really neat thing about his table, and I'll kind of skip ahead here for a second, was that as he was putting his table together, he actually left blanks, the way I understand it, because those particular elements had not yet been discovered, but based on those blanks and based on the properties and based on the similarities and based on the information that he put together, he actually predicted. So he predicted the existence of some of those atoms. And the really cool thing about it is that later on, he proved to be true. His predictions proved to be true. Now, we've actually, we've come a long way since this, but this is in its early beginnings, and we need to give Dmitry Mendeleev a lot of credit, okay? Now, the word periodic literally means repeated in a pattern. So when we say the periodic table, we are really saying that we have a table that is showing tendencies, but it's also showing items, different items, and we'll delve into some of those. But literally, they get repeated, but they get repeated in a pattern. And once you can recognize those patterns, and once you know how to use that information to your advantage, then this tool, this visual aid really starts coming to life. Okay? All right, so going back to Mendeleev just for a second, as he began to put his elements together, remember, he was doing it by increasing atomic mass. And if you look at the modern periodic table, it does very much appear that the table is put together by increasing atomic mass. Well, here's the problem with that. When you get to tellurium, right here next to iodine, okay, so number 52 and number 53, what do you notice? Well, you notice that it has a mass of 127.6. This has a mass of 126.9. So all of a sudden, we would have a very definite anomaly if we were going simply by atomic mass. Now, the real question is, why is tellurium here rather than here? Why aren't they switched? Well, one of the things you're going to learn, and we'll get a little ahead here, but you're going to learn that it had more in common with these atoms in this group than it did with the atoms in this group. Now, that's not really the main point that I want you to take right now, though. The main point that I want you to take is that we're not really totally following Mendeleev's early work. Why? Well, because we're not putting our modern periodic table together solely on atomic mass. We're putting the periodic table together on the increasing atomic number. So number 1, number 2, number 3, number 4, number 5, number 6, number 7, 8, 9, 10, so on and so forth. And as we already know, the atomic number is the number of protons. And that proton number gives that atom its identity. So the modern periodic table is put together by increasing proton number. So we are looking at the atomic number increasing as we go from left to right across a period. Okay? I'm going to tell you these are periods 1, 2, 3, 4, 5, 6, 7. As you go across, the vertical are called groups. All right? So we have a period. Okay? We have a period. And as we look one more time across the period, we see that the atomic number, or the number of protons, is increasing by a magnitude of 1, and you can easily see this. So 3, 4, 5, 6, 7, 8, 9, 10. All right, so we're going across the period, atomic number increasing by a magnitude of 1. Now, as we look at the periodic table, we also see something that we can refer to as periodic law. And what we see is we see that as we go down a group, okay, we tend to see properties repeated. Now, once again, I said a group, so vertical. What happens as we go across a period? We tend to see properties change. So going across a period, we tend to see changing properties. For instance, here we have into the second period, we would have some metals, but obviously we get over into here and we have non-metals. We would definitely expect a metal and a non-metal to have different properties. But as we go down, we notice that all of these are metals, and that's a little general. We would even kind of give some group names, but we're not ready for that yet. So as we go down a group, we tend to see properties repeat, okay? And a really cool property, and we're gonna look at this a little bit together in class, but the first group, oh my, these elements are extremely reactive in water, and they all share that similar trait. Well, that's something that tends to be periodic. Remember, periodic means repeated in a pattern. So within the periodic table, we tend to see items that are in a group have properties that tend to repeat. But as we go across, our properties tend to change. Okay? All right. Now, another item that we get from the period number, and remember something that I said earlier. I said, as you learn how to use the periodic table, as you learn how it's put together, as you learn different facts about the table, and you've got to learn those facts. But after you've learned a lot of this, you're going to be like, all of this information is at your fingertips. All you got to do is look. It's right there. Okay, so another piece of information that we would get from the period number, we would get N. And we already know that N is the principal quantum number and would tell us the principal energy level that we are in. So we're in the first energy level here, second energy level, third, fourth, fifth, so on and so forth. So from the period number, we can also ascertain the principal quantum number. Okay? All right, now when we just look at the periodic table sort of as a whole, then we see this red shaded area. We see these, almost like neon green, kind of almost in a stair-step line. And then we see this blue category. So what are we really kind of looking at this point? We're really just kind of looking at 3 chunks. All right, and so what are these? Well, color-coded, they are metals. What are these? As you transition from a metal to a non-metal, okay, you're transitioning. Remember, you're going from the left to the right, so you're moving across. We would have the metalloids. What do metalloids have? Well, I think you could probably already figure they must have properties of both metals and non-metals, and that would be true. Now, what about your blue category here? Well, that would be your non-metals. So really we have metals, metalloids, and non-metals, and then we do have a few that are what we call unknown. All right, but we really, honestly, in this class, we're not going to give much focus to those items. Not that they're not important, we're just not going to give much focus to them, okay? All right, now, I also want to add that you heard me say something a while ago. You heard me use the word transition. Well, I want you to think about this. As you go from one grade to another, what are you doing? You're making a transition. As you grow from your adolescent years into becoming an adult, you're making a transition. As you move across the periodic table, you're making a transition. Well, what do you mean you're making a transition? You're transitioning from metals into non-metals, okay? So we refer to these elements in here, we refer to them as the transition elements, okay? All right, now, we're going to give a general, very quick definition to metals, metalloids, and nonmetals. And here it is. If you are a metal, you're generally a good conductor of both heat and electricity, okay, or electric current. If you are a nonmetal, you generally are a poor conductor of electric current and heat. Now, what if you're a metalloid? Well, if you're a metalloid, then you find yourself somewhere in the middle, and it probably is going to be dependent upon the particular metalloid, and it's probably going to be particular upon that circumstance, okay? So I'm not going to say that they're good, bad, whatever. Metalloids have some properties of both, okay? And so sometimes what they can or can't do is going to be related to the conditions that you find them in. But for us, we're going to remember that metalloids have some properties of both. All right, but these are the general definitions that we're going to give to those three areas on the table. All right? All right, now this one is a little bit more involved. And a lot of times at this juncture, you know, I don't ask you to memorize just for the sake of memorizing. And sometimes I don't ask you to memorize what I can quickly pluck from a table. My preference would be that you know how to use the table rather than, I think, having the table memorized. Okay, I don't memorize tables if I can know and go and use the table. But when you look at this particular table, you'll see there's a lot of color coding. And that's because sometimes these groups, okay, or sometimes some of these sections have some further designations. And remember, why would they have those designations? Because they share similar properties. Okay, remember, properties are changing as we go across, but they tend to be the same or very similar within a group. So I would expect you to be able to know where the alkali metals are. I would expect you to know where the alkaline earth metals are. I would expect you to know where the transition elements are, or basic metals, or metalloids, or non-metals, or noble gases, or halogens, okay? Now, these are terms that I won't necessarily make you memorize, but I would certainly expect you to be able to go to a table, especially one that is color-coded, and be able to tell me where those particular groups of atoms are, okay? So that would be pretty simple. All right, now I don't mind you knowing at all that another item that you're very much going to look at in this classroom, especially when we work with bonding, we're going to talk a lot about the noble gases because they are, as suggested, gases, but they are called the noble gases because they tend not to make bonds with other atoms. Now, the reality of this is, and this is getting a little ahead of this presentation, but I don't mind if we kind of introduce the idea that these are the noble gases. They are gases, and they are called the noble gases because they have a full S&P orbital for that particular energy level. Now, I'm not going to ask you to know a lot about that right now, but I certainly don't mind if you know that. Let's start learning as much as we can about the information that is available to us on the table. All right, what else do we have? Well, we have a picture right here that I actually took next door in Mr. Coy's room. And this is a really cool kind of painting that's on his wall. And this is actually what the periodic table looks like if we don't pluck this out and put it down below. Now the question is, well, why do we pluck it out and put it down below? And the answer is just ease of use. It's about maximizing the space that you have available to you. It's about making things more compact. So this particular section right here, if it were placed in the table, this is what the table would look like. But when it is not placed within the table, then this is what the table looks like. And this is the lanthanides, okay? And these are the actinides. And this particular section of the table tends to find itself below the table. But if it were in the table in its proper place, then once again, it would look like that. Okay? So that's kind of interesting. All right? All right, now I also don't mind if you know that you can simply look at the periodic table to determine orbital chunks. So you get into your s orbitals here. Here, you're into your p orbitals. And here, you get into, and I did that wrong. And I'm glad I caught that right now. Let's change that. That's in the wrong place. Okay? So let's do this. And I'm glad, and I apologize, but that is not right. That goes right there. And that goes right there. Okay? So this is your S chunk, this is your D chunk, and this is your P chunk. All right? So I'm glad we caught that rather than having a mistake in the presentation. All right? And that is something that I certainly don't care if you know, and as much as you can start recognizing, that'll be a good thing. All right, now let's pluck one box off the periodic table, because obviously the periodic table is a bunch of these little boxes. What do I have? I have the atomic symbol. What do I have? I have the atomic number, which is the number of protons, as you well know. That is the identity of silicon. What do I have? Now, some of this information I won't necessarily have on every table. And a lot of times this number will be at the bottom, but these two numbers are sometimes flipped. Well, come on, common sense. The numerical order, 1, 2, 3, 4, 5, 6, 7, 8, increasing by 1, that's the way the periodic table is put together, so it doesn't matter where it's at, okay? This is the proton number or the atomic number. This is the average atomic mass because it takes into account isotopes. And you're going to have a whole presentation on average atomic mass, which you may have already had, so you understand this number is an average. Now, so what kind of information can I get from that box? Well, all I got to do is look at that box and I can tell you how many protons it has, I can tell you how many neutrons it has, and I can tell you how many electrons it has. And if I know where that box is on the periodic table, I can even tell you what energy level it's in, I can tell you what energy levels it's gone through, and I can give you its electron configuration based on its position. Okay? So once again, you know, we kind of think about the fill-up rule, we think about off-ball, we think about orbital notation, we think about a lot of things that we can do with this information, or a lot of things that we can know if we just have this information available at our fingertips. Atomic number, number of protons. Average atomic mass, number of protons plus neutrons. If this is electrically neutral, this will be the number of protons and the number of electrons. If I want to know my number of neutrons, I do a simple subtraction, 28 minus 14. Now, I'm not going to write down for my number of neutrons 14.09. I mean, how am I going to have 0.09 of a neutron? What am I going to write down? I'm going to write down 14. Why is this not an even number? Because of isotopes. Okay, it's an average atomic mass. All of that information is available to me on the periodic table. So once again, if I have my symbol, if I have my atomic number, and I have my average atomic mass, then I can do some simple subtraction to get my number of neutrons. I know that 14 protons will be 14 electrons if it is electrically neutral. And I already knew this because this was printed right there. Because that is what gives this its identity. Okay? And it's all there on the table. Now, are there any other tendencies that might be reflected that you probably need to know about, but yet you might not readily recognize? And the answer is yes. In this classroom, we've already talked about atomic size, literally being, in this case, not how much stuff you have, but how much area you're taking up. And we realize that there is a property in atomic size where as you go across a period, okay, your size literally decreases, but as you go down a group, your size increases. Now, why is that? How can that possibly be? You're adding more protons and electrons in the same principal energy level. So you are increasing the number of positives and negatives. So you are increasing, the attractiveness, which is going to decrease the size. Now, why does it increase as you go down? Because of what we call the shielding effect, okay? You're literally shielding, okay? Each subsequent level is being shielded by the one below it, all right? Now, we've talked about this in class, but this is a tendency that is reflected indirectly rather than directly. So this is something that you learn, and it kind of supplements your knowledge of the periodic table. Now, I do want to add one quick thing that I may not have told you up to this point. When we talk about atomic size, we're actually talking about R, okay? We're talking about two atoms of the same type bonded together. The distance between their nuclei would be D, okay? But we're only going to take half of that. So atomic radius is 1/2 of D of two atoms of the same element bonded together. Now, then if we talk about size, what we're really doing is we're talking about atomic radius. What's the point? Well, the point is like everything else in science. We've just developed a standard, a way in which to talk about size. So when we talk about size, okay, we're actually talking about R. And R is 1/2 of D of two of the same elements bonded together. Okay? So that's the reference point that we're making. All right? Are there any other trends that are maybe not necessarily immediately evident that we might want to know about from the table? And the answer is yes. Electronegativity. Electronegativity is an atom's ability to attract electrons. As you go across the periodic table, so as you go across a period, electronegativity increases. As you go down a group, electronegativity decreases. Now, this is a very important fact and something very important to know because it puts some of the most electronegative elements of all right up in here. And when you learn more about bonding, when you learn more about bonding types, this information will become very important to you, okay? But this is something that you're learning along with your knowledge of the periodic table, and once you know this fact that you learn, then it makes your periodic table even more powerful because it's just more and more and more information that you're learning that you can get straight from the table. Don't forget, periodic means repeated in a pattern, okay? And then the last thing that I'm going to throw at you today, and I'm not really going to teach you much about it, I'm just going to throw it out at you, is something called valence electrons. And valence electrons are easy to get, especially for these two columns and these 6 columns. Okay, you notice I blocked out the transition elements. They're kind of a different ball of wax that we'll talk about. But if I want to know the valence electrons for these columns, I'll tell you how easy it is. It's this easy. I just count 1, 2, 3, 4, 5, 6, 7, 8. So how many electrons do these have in their outer energy level? They have 1. They all have 1. That's why they're in the same column. How many here? 2, 3, 4, 5, 6, 7, 8. And what do I know about noble gases? I know they have a full S&P. Well, that's 2 plus 6 equals 8. And what do I know about them? I know that they are unreactive. And I know that these other elements are willing to make bonds to become like these guys. Okay? But that's a discussion for another day when we talk about bonding. For now, the last fact that I'm throwing out at you is that it's easy to get valence electrons. All I got to do is count. So these are some introductory facts about the periodic table. How do you eat an elephant? One bite at a time. Here is your first bite about the periodic table.